Okay? So how do you derive, how do you predict what the rate law is going to be given a mechanism for a multi-step reaction? Okay, like I said, your reaction order has to be experimentally determined, but with a proposed mechanism, you can predict what the rate law would be, and so that prediction should be consistent with the experimentally determined rate law. And one thing you realize is when you start proposing mechanisms is that there might be more, typically there could be more than one mechanism that would be consistent with the rate law. Okay? And that is why you cannot use a rate law to prove a mechanism. You can just say, okay, this mechanism I'm proposing is consistent with that rate law. Somebody else might come up with a different mechanism and say, my mechanism is consistent with that rate law. So the question is which is which. There would be other experiments you'll have to do to determine how, which mechanism is more plausible. Okay? And multi-step reactions also, one thing you'll find is they may not always have simple rate laws. Okay, so you might have fractional orders, you might have the concentration of the reactant in a denominator in your rate law expression. Okay, so let's look at just some simple mechanisms. And let's look at the simplest type is one where you have a series of steps, but the first step is the slowest. So that's your rate determining step. Okay, so for example, this particular reaction here, 2NO2 plus F2 gives you 2FNO2. If you did the experiment for this, you'll find that the rate law is this one. Rate equals K times NO2 times F2. Right away, look at that. Look at that rate law. It's only first order with respect to NO2, although your coefficient for NO2 in your balance equation is 2. Right there and then, that tells you this can't be a one-step mechanism, right? This can't be a one-step reaction. So what kind of mechanism would lead to this type of rate law for this overall reaction that we have here? So here's one possible proposed mechanism. The simplest one you can propose, okay, is one where there's a first step that is very slow compared to all the other steps. So that step you say is your rate determining step. That determines the rate of the reaction. And so the rate law will just reflect the rate law for that particular step. So that's a very simple case. So here you're proposing that NO2, one molecule of NO2 collides with a molecule of F2, and what happens? What happened here? This F2 apparently split up, right? One of the fluorines attaches itself to the NO2, and then that leaves the other fluorine atom. So you have a collision between these two molecules, and we're proposing that that's a slow step. And then we propose in step 2 that this fluorine here, that's produced in step 1, finds another NO2 molecule really fast and gives you the other product, FNO2, another FNO2 molecule, and that's fast. And so step 1, we say, since it's slow, will be your rate determining step. The rate law for the reaction would just say that the rate is equal to the rate of step 1. What's the rate for step 1? It's just K times concentration of NO times concentration of F2. So that's your rate law. That would be consistent. So F here, what do we call F here? It's not a reactant, it's not a product, right? That would be what you would call a reaction intermediate. Okay? So one evidence you one experiment you might want to design in the lab, if you want to further investigate the plausibility of this mechanism, is you go design an experiment that would allow you to detect those fluorine atoms, the reaction intermediate. Okay, so let me give you an analogy for this to make it easier to remember. Let's say the rate at which you produce a hamburger. Okay, so your first step is you put your patty on the grill. Takes a long time to cook that, right? Your second step is you put the patty between a pair of 2 slices of bread, right? Inside your bun. Put the patty in the bun. How long does it take to put a cooked patty in the bun? 2 seconds. How long does it take to grill your meat? Several minutes, 30 minutes. It depends on whether you want it well done or raw or rare, right? But it takes longer to cook the hamburger, the patty. So step 1 is very slow. Step 2 it doesn't really matter, right? Or, I mean, the rate at which you can produce your hamburger would be dependent only on how fast you can cook your patty. Okay? What would be the experimental rate law that would be consistent with this mechanism? You're proposing that step 1 is slow, step 2 is fast. What would be the rate law for this mechanism that you would observe in the lab if this was the mechanism? What's the rate law for this reaction? Okay, very good. Correct answer is A. Why A? That's your slow step. The rate for step 1, so rate for step 1, and let me call that V1. V1 is K times NO2 squared. What's the rate for step 2? Is K times NO3 times CO, right? But it doesn't matter. Step 2 doesn't matter as far as the overall reaction is concerned because it's very fast compared to step 1. So we say the rate determining step is step 1. It's step 1 that determines what the overall rate of the reaction is. We say that is your rate determining step. So A is the correct answer.